the last lecture, we saw how a complicated integral operation like the convolution in time domain is simplified in the transform domain by the pure multiplication of the pertinent transforms. Let me illustrate this first with an example before we go on to a discussion of other properties. Let us consider a f of t which is a pulse of height half and lasting from minus 1 second to plus 1 second. I will call this f of t. Its Fourier transform f of j omega from our earlier discussion will be, if the amplitude is a and the pulse duration is d, a d, that is half times 2 1 sin omega d upon 2. So, if d is 2, d upon 2 is 1, therefore, sin omega divided by omega d upon 2, it is omega. So, in the standard terminology, if we had a height a and duration d, it would be a d sin omega d upon 2 by omega d upon 2. Now, a d happens to be 1 and d happens to be 2. This is the Fourier transform of this pulse. Now, what I would like to know is what is the Fourier transform of f of t star f of t, that is f of t convolved with itself. So, if I want to find out f of t convolved with itself, then first of all I write this is, let us say, f of x as a function of x. So, in order to find f t convolved with f t, I should take the integral of f of x times f of t minus x dx, that is the integral that I should work out. So, if this is f of x, this also happens to be f of minus x. That means, if I take another curve like this I can consider to be f of minus x, but I have to multiply f of x by f of t minus x. That means, this minus f of minus x curve I must push forward by an amount equal to t. So, that would be obtained by, let us say, this curve which I would like to say is f of t minus x. So, originally this was minus 1, this is 1, and I push this forward by an amount t, therefore, this interval equals t. So, the overlap interval between f of x and f of t minus x is, this is 2, this is t, therefore, this is 2 minus t. So, that is the overlap interval between these two, and when you multiply these two curves, each of amplitude half, you get the area under the curve. After all, this represents the area under this curve, and this is the area that you get. Amplitude is, the height is 1/4 and the duration is 2 minus t. Therefore, the area of this will be 1/4 times 2 minus t. That would be what would be the value as you push forward this curve in the positive direction. If you push it in the negative direction, you get a similar expression. Therefore, the variation of f t convolved with f t would be, for positive t, when t equals 0, we have to take these two, the f of minus x and f of x multiplied together, that will be 1/4 lasting for 2 seconds, therefore, it will be half, but then as t progresses, this reduces in this manner. So, it starts with half and becomes 0 when t equals 2, and beyond t equals 2, this white curve comes away from this, and therefore, there will be no overlap area, and therefore, it becomes 0 from that point onwards. And if you proceed in the negative direction, you get a symmetrical result. It can be easily be seen that this is minus 2. So, f t convolved with f of t will be having, if you call that g of t, this will be the variation of this. So, to find the Fourier transform for this, you do not have to spend any additional effort, because we know the Fourier transform of f of t. So, g of j omega, the Fourier transform of this is obtained by multiplying f of j omega multiplied by f of j omega, which is indeed sin omega by omega whole squared. So, you can find the Fourier transform of this as the Fourier transform of the convolution of a rectangular pulse by itself. So, you can independently get the Fourier, calculate the Fourier transform of this, and you can show that this is indeed equal to this. We will next study the rule corresponding to integration in time domain. You can recollect that we said when a function is differentiated in time domain, in the transform domain it gets multiplied by j omega, and at that time I observed that if you want to integrate a function in time domain, in the transform domain it is not nearly division by j omega, it may entail something else. Let us see how that works out now. What we in particular we like to work out is, given f of t and f of j omega as a transform pair, what is the Fourier transform of integral of f of t dt from minus infinity to plus infinity, minus infinity to t. So, this is a function g t which is obtained by integrating f of t from minus infinity to t. You can see that minus infinity to t of f of t dt can be written as minus infinity to infinity of f of x. I can write this also as f of x, no problem. This can be written as, after all this is a dummy variable, so I can write this as f of x dx. I can write this as f of x times u of t minus x dx, because what happens when x goes beyond t, when x is more than t, t minus x is a negative quantity, therefore, this becomes 0. U of t minus x is 0 for x greater than t. Therefore, in this range of integration, whenever x exceeds t, it is the integrand is 0. Therefore, instead of confining our integration of minus infinity to t, we are nominally taking this the upper limit of integration to plus infinity, but we know the value of this integrand from t to from x equals t to x equals infinity is going to be 0. So, these two are equivalent. That means, to this I am adding something which is equal to 0. So, both are equal, and you can see that this is immediately equal to f of t convolved with u of t. After all, that is the formula for a convolution of two time functions. F of t convolved with u of t will give me this. Therefore, we observe that integral of f t from minus infinity to t is equivalent to convolving f of t with u of t. And we know from the convolution rule that the Fourier transform of this is obtained by multiplication of these two Fourier transforms. The Fourier transform of this will be f of j omega 1 over j omega pi delta omega, that being the Fourier transform of the unit step function. So, the Fourier transform of this is given by this. You observe now that f of j omega is not merely divided by j omega, but you have an additional component f of j omega times pi delta omega. So, this is the important result that we have. When you want to integrate a function of time from minus infinity to infinity t, you have to multiply by 1 over j omega plus pi delta omega. Let us see the implications of this. Is this compatible with this differential? Is this compatible with the rule for differentiation, which we have already talked about? That question we would like to settle first. What we are saying is, if g of j omega is from minus infinity to t of, I am sorry, g of t, suppose I write g of t, I define this as g of t, f of t dt, then we know the derivative of g t with reference to t is f of t. Therefore, if the Fourier transform of g of t is g of j omega, then j omega multiplied by that must be the Fourier transform of f of t. Hence, j omega times g of j omega must be equal to f of j omega according to the derivative rule. According to the rule for differentiation. Now, is it indeed so? So, we know that g of j omega has got this Fourier transform. Therefore, let us see, check this. J omega multiplied by f of j omega multiplied by 1 over j omega plus pi delta omega. If you take that, the product of f of j omega, 1 over j omega and 1 over j omega gives me f of j omega, plus I have additional term which is f of j omega pi delta omega. Now, what we would expect is this should result in f of j omega, but we have an additional term, but we observe that omega times delta omega is 0, because any function delta omega multiplying delta omega will be equal to that function evaluated at omega equals 0 multiplied by delta omega. Therefore, since this quantity goes to 0, this is indeed equal to f of j omega. Therefore, there is no incompatibility, this is quite all right if it is consistent with the rule for differentiation that we have already derived. So, the summary, in summary, the integration in time domain from minus infinity to t of f of t dt is translated into the transform domain as multiplication of f of j omega by 1 over j omega plus pi delta omega. However, we observe that for a special case, if I can write this g of j omega, which is the Fourier transform of this quantity, is f of j omega divided by j omega plus pi delta omega f of j omega. So, special case of f 0 being equal to 0, suppose we have a special case where Fourier transform evaluated at omega equals 0 is equal to 0, then this will be 0, because this is equal to pi delta omega f of 0, and in this case this is equal to 0. Therefore, f of 0, if it is equal to 0, then the integration will result in f of j omega by j omega, you do not have the extra term. And when does f 0 become 0? Then you recall once again f of j omega equals f of t e to the power of minus j omega t dt minus infinity to plus infinity. So, f of 0 will be minus infinity to infinity f of t, when omega equals 0, this is 1, this is equal to this f t dt. So, the summary of this is if f 0 which is equal to minus infinity to plus infinity of f t dt is 0, then the Fourier transform of f t dt is simply f j omega over j omega. The second term drops out. So, to summarize, in general whenever you have an integral from minus infinity to t of f t dt, its Fourier transform is obtained by multiplying f of j omega by 1 over j omega plus pi delta omega. On the other hand, for the special case where the integral of f t dt f t from minus infinity to plus infinity is 0, which is f 0, if that happens to be 0, then the Fourier transform of this integral will be multiplied by f, will be obtained by multiplying f of j omega by 1 over j omega. Let us work out an example illustrating the integration rule. Let us consider an example to illustrate this. I will start with an f1 of t which consists of a pair of impulses of strengths A and minus A at minus d upon 2 to plus at d upon 2. This is f1. I obtain from f1 a function f2 which is the integral of f1 from minus infinity to t. So, as I integrate from minus infinity, I pick up 0 area. At this point I have a jump and the jump is equal to a, and that continues up to this point, and beyond that you have another jump of minus a because you are integrating through an impulse, and therefore, this becomes 0. So, this will be f2 is obtained by integrating f1 from minus infinity to t. Therefore, what we have is this kind of f2, the derivative of f2 is of course f1. Now, if I integrate this once more, I get a function f3 which is minus d up to minus d upon 2, this is 0, and then it gradually increases because you are picking more and more area under this pulse. Therefore, this increases like this up to d upon 2, and beyond that it is flat because there is no further area being added to this curve. So, that will be the nature of f3, and the total area picked up from this point to this point is a times d base area. Therefore, this is equal to a d. Now, our interest is to find out the Fourier transform of such a curve like this f3. Now, we can put the problem this way. Suppose we want to find the Fourier transform of such a curve like this, then you know that this is the integral of this, which in turn is the integral of this. So, if you can find the Fourier transform of that, by integration rule you can find the Fourier transform of this, and by the integration rule again you can find the Fourier transform of this. This is what we want to do. Our motivation for doing this is the Fourier transform for this is very simple, because it consists of a pair of impulses. We know the Fourier transform of this is a 2 pi a. The strength is I am sorry, the is impulse of strength a, therefore, a e to the power of j omega d upon 2 representing this pulse, and this is minus a e to the power of j minus omega d by 2 because it is shifted in time by d upon 2 seconds, and this is negative, therefore, minus j omega d. So, this is the Fourier transform of this. Corresponding to this impulse of strength a, you have Fourier transform of a, but since this is advanced in time, you have to multiply by j e to the power of j omega d upon 2, and since this is delayed in time, you have to multiply by e to the power of minus j omega d upon 2, and since the negative impulse, you have minus sign here. and this of course is equal to 2a sin omega t upon 2. Now, when you come to this curve is obtained by integrating this. Therefore, you have to multiply this by 2ja sin omega d upon 2 multiplied by 1 over j omega times pi delta omega by the integration rule that we have just now observed. And here is a case where the integral from minus infinity to plus infinity of f1t is 0. In other words, f0, the value of this evaluated at omega equals 0. Therefore, this term drops out. We can also verify this from substituting omega equals 0, this quantity is 0, that multiplied by pi delta omega leads to 0. Therefore, you get contribution only from the product of this term and 1 over j omega. Therefore, that will be 2a sin omega d upon 2 by omega. 2a sin omega d upon 2 by omega, which I can write this further as ad sin omega d upon 2 divided by omega d upon 2. That is a form with which we are familiar. I just wanted to put it in that form, so that once we have this pulse function, we know immediately its Fourier transform of this. Of course, the same thing is obtained through finding out the Fourier transform and derivatives to start with. Now, the Fourier transform of this is once again obtained by multiplying ad sin omega d upon 2 divided by omega d upon 2 by 1 over j omega plus pi delta omega. And now, f of 0 of f2 of 0, capital F2 of 0, that means Fourier transform of this evaluated at omega equals 0 is not 0. Therefore, the second term also has its place, it is not going to vanish. Therefore, if you write this, we can have first of all the product of these two, delta omega multiplied by a certain function is equal to that function evaluated at omega equals 0 multiplied by the delta. So, omega equals 0, this becomes ad times pi delta omega, because sin omega d upon 2 by omega d upon 2 evaluated at omega equals 0 equals 1, and then you have 1 over j, I put this as a minus j, ad is already there, sin omega d upon 2 divided by omega, because this omega is there, another omega d upon 2 is there, omega squared d upon 2. So, that will be the Fourier transform of this. So, this example illustrates how one can repeatedly differentiate a function or integrate a function and then get one transform from the other using the rule for differentiation or the integration, as the case may be. Earlier, we had worked out some examples where a function was continuously differentiated. Now, we have taken a reverse order. We started with a simple function whose Fourier transform can easily be obtained and integrated this in 2 successive steps, and therefore, from the Fourier transform of this, we are able to find the Fourier transform of this.